Okay, this is about dilations and kind of putting it all together, because once we have dilations from geometry, we can have all the tools from the algebra and we can kind of put everything together. The only other one after this is lesson 7, which is about inverses, and that's going to seem really easy because we did a bunch of inverse stuff back in the unit on logs. Okay, so this is about locating images and pre-images of figures by dilation. So we've done reflections, translations, and glides, and those were isometries, and isometries were nice because they preserve distance and area and congruence and angles and all that stuff. But for the first time ever, we're going to have dilations. See what I'm doing there? We're changing the size of something. That was just a little technology trick. And when that happens, we end up getting something that is similar to what we started with, not congruent. And we've used words before like scale factor, so that shouldn't seem too crazy. What might seem, I don't know, what's also important about dilations is that the other detail has to be a center. So when we blow something up, like right now, I can do this right now. I'm going to kind of center my pinch right here, and I'm going to blow up and kind of zoom in on that pinch. Notice kind of where everything goes. But if I started here, instead of having my center there, if I had my center kind of, I don't know, over here, and I zoom in on that, that sends things to a different place. So not only does the amount of scaling make a difference, but the center of the scaling is equally important. So just like rotations, they have a center. All right, so dilation here, and here we go. The dilation 0, O, k has a center at 0 and a scale factor of k. It takes any point and blows it up kind of away from point O by multiplying by that factor. And I'm sure that makes total sense because we've already done that with similarity back in Unit 5. And yeah, so there's some technical details here about how it actually works, about the opposite ray and that kind of stuff if it's negative. But if you just think number line, I think in the examples we'll get to it. But basically, it's like you think of the center point as the 0 on a number line. If I have to take point A and I'm going to dilate this thing from center O by factor of k, I measure here from O to A, whatever that distance is, and then I multiply that by, so let's say this is 5 centimeters, and let's say k equals 2. I multiply that by 2, so we'll be talking about 10, but I still think about this as the 0, and I think about the same number line kind of going that way, as if I had my ruler laid down there. I always keep this as the 0, and if I measure to 10 on that number line, you can see it would be kind of over here somewhere, so A would go that way. This business about the negative dilation, I guess that's kind of new compared to geometry, would be like, well, what if we use -2? Same everything, but if we had k as -2, then when I take 5 and multiply it by k, now 5k is going to be -10. I'm still using this point as 0 on my number line. The ruler is still lined up the way it was, but now -10 on the number line is going to be kind of over here somewhere. So -10 just means kind of go backwards the other way. That's what they mean here by opposite ray. Okay, I think it'll show up in the examples, or at least we'll do it. If I don't do it in the examples, we'll make sure we do it early in class about the negative. What's going to happen after all that is you're going to, like if we do this with triangles, or if we do this with rectangles or quadrilaterals, we're going to produce similar figures. We're going to get 2 triangles or whatever that are similar, and they all maintain that same scale factor, and all of their length changes. Okay, if k is greater than 1, we call it an expansion. Even if it's like -5, we call it an expansion. In other words, I wish they would have said this. If the absolute value of k is greater than 1, we call it an expansion, because the thing gets bigger. If it's negative and bigger than -1, it kind of looks like it rotates around and gets bigger, but it still gets bigger. But if k is between 0 and 1, and again, I wish they said the absolute value of k is between 0 and 1, the thing is going to look like it gets smaller, and we call it a contraction. Yeah, so they talk about the negative here, and I kind of said that already. Okay, so let's do one. Can I use a ruler? I want to try this. Just a second. Okay, I don't know if you can see this ruler or not. I don't know if it shows up in the video or not, but I figured out how to lay a ruler on here. So this is going to be, my ruler doesn't have points. That's going to be the 0 of my ruler. I can measure, and I think it just makes it so my pencil kind of slams against it. Is what this ruler does. But I'm going to measure from here. Oh, weird. It kind of sucks the pencil line into there. From there, I'm going to measure that, because we're supposed to do dilation of scale factor 2. Measure this, and then I'm going to multiply that by 2, and then measure from here out by a factor of 2. Let me get rid of that ruler because it's just kind of bothering me now. But that's what it should look like when you lay it down. Okay, so I got the ruler out of there. Hopefully that didn't mess up too much. So B is going to end up somewhere like this, Now I'm just going to kind of eyeball it. Actually, I could get a real ruler out. Give me a second. So I have a real ruler. I'm laying it actually on my iPad, and I measure from O to C. I measure how far that is, and then I go twice as far out the same way. It's something like here for my C prime, and for A, I'm measuring this way, and I go twice as far down that way, and I get something like, I don't know, around here. This isn't perfect, but I'm trying to kind of go fast. Whoops, things are moving. And so my new figure looks something like that, my new triangle. And as we see, like it retains some properties here. Sorry, this is just getting in the way now. I can't erase. Well, that's weird. Okay, that's erasing. Sorry. That we can see that like if this was, I don't know, 5 centimeters, that ought to be 10. And if this was 6, that ought to be 12, kind of thing, because we dilated by a factor 2. The angles will stay congruent, as we would expect, and we have a similarity transformation. Okay, moving on. Draw the pre-image under this thing. I am going to do this one in class. Well, this will be one of the first ones we do in class. It's just the same kind of thing, but we're just going to go backwards. All right, next page. Coordinates. If you were to use coordinates to dilate stuff, you would see that if the center is 0, 0, which is really nice, notice they're saying if the center is the origin, then what happens is the dilation of scale factor k is simply multiply the coordinates by k. Again, that only works if your center is the origin, which most of these will be written as. I could see some level 3, level 4, hint, hint, wink, wink, nudge, nudge if it was centered somewhere else, but centered at 0, 0, you just multiply by k and life is easy. Okay, so let's do some of that. So we're going to say find the image of ABC if we center at the origin and multiply by -half. Okay, so this coordinate here at C has coordinates at 0. Can I erase that really quick? My eraser did some weird things last time. Okay, it's fine. This was, if you want to think about coordinates as you do this, this is 0, 3. So when I multiply it by 0, -half, that 0 should stay 0, but the -half turns 3 into -3 halves. So it's right about there. You can also think about this in terms of the geometric definition of dilation. This point was 3 kind of north of the origin, and if I multiply that by -half, it should go -1.5 in the other direction. So I think that kind of makes it easy too. Let's do another point. I think this is all going to be in the way. You can pause that and bring that back if you want to. But point C, I lost my point C. Point C prime is kind of right here. Point A, again, I'm thinking A is this far. I'm going to do the geometric way. A is that far away from the origin that way. Half the other direction, like half as far away and the other direction is there. My pencil gets skinnier when I zoom in. It's very strange. And B was here. I'm going to go half as far back in the other direction. I think that would be right there. So my triangle looks like this for A prime, B prime, C prime. C prime just really thick because of similarity things that are happening. Woo. Okay. Find the scale factor dilation from, what? Oh, find the image in the I wrote this in the wrong place. Find the image and find the image of A prime, B prime, C prime. I just did part A. Find A prime, B prime, C prime under DO -4. Let's change colors. We're going to do this in a different color. Okay, still using a different software than I started out using this semester, but I'm getting used to it. I like the video qualities of this better. All right, scale factor that takes the original and goes by a factor of -4 on that one. Okay, so -4 from C, I got to go towards the origin, keep going twice as far the other direction. I'm going to get down here for C double prime. That takes the original, right? Yeah, okay. A, I'm going backwards. I'm going 4 times as far. That's going to go off the page, isn't it? If I go 1, 2, 3, 4, I guess not. A double prime's right there. And you can do that with coordinates if you want. Okay, let's talk about that one with coordinates. This is -2, -4. If I multiply those by -4, I should get positive. What? Did I do that wrong? I did do that wrong. I only went 2. I did not go far enough on that. -4. Wow, that is way off the page. That should, I just went twice as far because that's, I did -2. -4, A prime is going to be way up here somewhere at -8. Sorry, not -8, +8. +8, +16. So it's kind of like up here in the other theorem somewhere. And then B was at, so I'm glad I did that with coordinates. -4, -2. B is going to be, is that going to fit on the page? That's going to be at +16, +8. I think that's also off the page. So we're going to have this ginormous triangle kind of out here for the double primes. find the image of B. So that's actually a terrible drawing. But you have to realize it is huge and kind of off the charts. Find the image of point B after dilation of A2. Well, you know what? I'm kind of done with trying to fit this on the graph. Actually, with 2, it's not too bad. After dilating that, oh, center at A, that's the new part. That's weird. Okay, now I kind of have to look at this. Point A was here. That's now the center. I really kind of have to use my hands and count now. 2. So if it has a dilation factor of k equals 1, it stays exactly where it is because I would just multiply that by 1. But I am multiplying this by 2, so I go just as far. I kind of keep going 2 times as far now from where we started, and now this is the answer to this. It didn't tell me what to label it. There's already a B and a B double prime and a B single prime everywhere, so yeah, this would have been B double prime over here. Let's just leave that as it is. Oh, example 4. If D blah 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 maps that to that, okay, that looks like a good class time thing to do. We will do that one in class. Okay, and this is the algebra one, or the algebra part of this. And it says stretch, compress, translate. Stretch and compress kind of go together. Now that we've seen all this in one, let me just say this again. We're always going to think of this in order of R, S, T, and this is reflect, and this is stretch, and this is translate. And stretch and compress is kind of the same thing. That's kind of one of the types of stretching. Okay, let's go on. Okay, this is part of 1.3. This is how I've chopped up that section from. I chopped up that section from what do you call it? Algebra 1.3, and we are getting to the part where we're multiplying out front here now. So this is a times fx. You know what? I think I might even just show you this now. Never mind, it's on the next page. It'll do something weird. I had that formula on the board where I had the A and the B and the H and the K all in one place. We're finally getting to the A and the B now. So this is going to have some familiar surprises in it, I guess is what I'm gonna call that. Okay, so if I take the original, which is this solid kind of one, and I multiply all of those original ones by 2 kind of on the outside of f of x. F of x happens, and then we multiply that y result by 2. Look at what happens. It says, what they want you to say here is just kind of like, what does this look like in words? So we originally have this kind of thing right here, that little check mark thing that I've highlighted in red, and if it turns into this yellow one, what's really going on there? Well, hopefully you can kind of tell that what's happened is, and if you think about what happens when we multiply by something by 2 out front, it's taking that y-coordinate and multiplying by 2. So all the y-coordinates are getting twice as far away from 0, 0. They're getting twice as extreme as they were. This this y-coordinate was 3, it has become 6. This y-coordinate was -4, it has become -8. So this is what we're going to call because it's growing, wish you could see my hands. It's growing vertically. It's kind of growing. The tall gets taller, and the short gets taller, and but the negative stuff below ground goes farther below ground. It's getting more extremely far away from the y-axis. We're going to call that vertical expansion. And just like we did last time, we're going to save this one for when we're in class. But let's keep going with this. Oh yeah, there's a table kind of discussion of what I was just talking about. So if we multiply by a number out front, it's the amount of vertical expansion. What if we multiply by something on the inside? Well, let's look at what happens if we multiply by that 2 on the inside. Something totally different happens. You can see some colors in here now. Yeah, this x-coordinate that was, and we're talking about, you notice what's happening here if you just kind of look at the picture. What's happening here is the x-coordinates are changing. If you look at what's happening down here, the x-coordinates are changing. So let's talk about this, kind of different from what we just did above. Let's talk about this in an x-coordinate kind of fashion. What's happening here is the x-coordinates with the times 2, notice, the x-coordinates are getting closer to the x-axis. So we're going to call this, like things are getting smashed in the elevator doors, we're going to call this horizontal, because that's the direction of the motion here. Horizontal compress. Oh, and I could say I'm horizontal compressing by 2. Well, we'll say this in half, or say this in class. I could also see someone saying that that's by half. We can argue about this later. I would take it if you said it either way. And like all these things, I don't really care how you say it. I care what you graph and what you code and what it looks like. I guess I could have set up here vertical expansion by 2. I'm gonna call this horizontal. Compression, I can see people saying compressed by 2, like we've made it twice as small. I don't know, some people talk that way. Or say by half, because we've made it half as far from the x-axis as it was. Anyway, the big distinction here is if you multiply by something out front, it's going to make it grow up and down, and if you multiply by something on the inside, it makes it grow kind of left to right, kind of smash it into the center. But as we said before, things on the outside, such as multiplying or even adding, and change the y position of things in a predictable way, whereas multiplying by things on the inside kind of change things in an unpredictable way, right? Like how come my eraser just all of a sudden doesn't work all the time? Yeah, weird. It changes in an unpredictable way. So we're multiplying by 2 and it's actually getting smaller. It feels like it's getting closer in, where this multiply by 2 may get bigger and farther away. So again, that's consistently surprising, hopefully, from what we did with translations. And yeah, that's why they always say, "Are you surprised? Are you surprised?" And I just kind of talked about that. Describe the translations that would make f of x. I'm looking at this next thing. I'm thinking maybe class. Describe the transformations that would map f of x onto the graph of that. Yeah, we'll do that in class. We could put them all together now. Here we go. So here they all are together. This is the thing I was talking about. That's kind of a major, I don't know, one-stop shop to see everything all at once. And this lists all of the different things in one kind of big table. So there's the reflections, and I like how they did this over here. They say dilate. I don't really love the term dilate here because of the geometric term we have for dilate. I can get into this in class, but dilate in geometry strictly means we have to go in the x direction, like in all directions the same amount, and they kind of are splitting horizontal and vertical, so I kind of wish they didn't use the term dilate, but that's the geometry snob in me. Is my eraser back? Oh, it is. Okay. So yeah, here they all are. We did this before. This is the translations. I kind of wish they did. We did this before. We used minus, and we said that we just kind of described it the other way. But they're still saying left and right here correctly, so it's okay. You can change the way you decide to memorize that if you want. But yeah, there's some patterns here. Things that happen on the inside of with x, like things that happen on the inside, like that and that and that, affect kind of the left and right things, and they affect things in a surprising kind of way. Whereas the things on the outside, like that and that and that, are the things that affect the y coordinate more, and they affect them in a non-surprising way, like multiplying by a makes it bigger, and adding k makes it go up. Whereas inside, multiplying by a big number b makes things smaller, and adding a positive number h moves things to the left. That feels backwards. The reflections, I guess, aren't terribly surprising. There's a reflection for x and a reflection for y, and one's on the inside and one's on the outside. And if you forget that, you can just use your hands and your imagination and kind of figure it out on the spot. That's what I always do. I can never memorize those things. Speaking of memorizing these things, these are not on the formula sheet or the theorem list. These are not theorems. These are concepts you're supposed to be able to internalize. Okay. I guess we should do example 3. We haven't done anything kind of like this yet. All right. The 0.25 is, oh yeah, we did this in the warm-up a couple days ago. And this is where we were supposed to learn how to do that. The warm-up we did in the other class was from 1.4 in algebra, and this is actually from 1.3, so that's why it kind of went that way. So so this is telling us basically that f of 2 is -5. That's all I know about this function. I need to make this work, knowing only this piece of information. I need to kind of expand this, or like translate. Maybe translate's not a good word. I need to find the analogous corresponding input-output that will make this work. So we have talked about this before. Essentially what has to happen is this thing that's going in here, inside f, kind of the input for f, I have to invent an x so that this part all becomes 2, because I only understand what happens with f if the input is 2. So I got to make this input 2. So I need 3x, with parentheses there, plus 4 to be 2, which means x plus 4 has to be 2/3, really? Yuck. So x has to be 2/3 minus 4. Is that -10/3? This is 12/3. 2 minus, what? -10/3? Am I right about that? Pause. Yeah, I decided I'm right about that. Okay. And then when I put in a -10/3 here, yuck, that is going to mean that this whole thing calculates out to be 2, which is great. And then at that point, the next thing that's going to happen is f of that, negative f of that minus 2 is what I'm trying to calculate for y. But when this comes out of the f function at this point, it comes out as negative 5. So I put in negative 10 thirds, becomes f of 2, and I did that because I know what f of 2 does. It's the only place where I can say something and go, ooh, I know what to do. F of 2 is negative 5. So now it's negative 5, and this becomes 3. So the point that's associated with this is when x is negative 10 thirds, y turns out to be 3. So the analogous point after everything is said and done, is the point negative 10 thirds, comma 3. That's the point it's the only thing I know that happens with this thing. Could I have done that with transformations? Let's talk about that with transformations, because we can do that now. We couldn't have done that a few days ago. So let's just kind of start over here a little bit, and let's talk about this. If I think about, I need to see all this now. If I think about how this function works, oh, I lost my eraser again. Weirdest thing. And I magically gotten it back. I think I'm starting to figure out the tricks of this software. Okay. Is that this whole thing should have, let's think about the reflect, stretch, translate involved with this thing. I have a reflection over the y-axis, is that right? Oh, it's right there, good. And then I have a stretch of a 3, that's the only stretch I have going on. Notice how the parentheses are very tricky here. If I wrote this as 3x plus 12, I couldn't read the 4 as a translator correctly. Anyway, what did I say? I have a reflection of the y-axis, and then I have a stretch that has to do with the 3. That stretch that has to do with the 3, if I look up here, that's the stretch of that one. Oh gosh, losing it. It's this kind of stretch. So this is a vertical. Yeah, no, I'm sorry, it's on the inside. It's that kind of. It's a horizontal compress. Horizontal compress by 3. You can call that 1/3. I'd be okay with that. There's no vertical expansion or contraction. And then I have a translation. I have a translation of, oh, I did my reflection wrong. I just happened to glance at that, and this is a mistake. Oh, why do I keep losing the... Oh, no. This is an X. I've lost it. This is a reflection in X. I'll just obliterate it. Yeah, if the F is, if it's on the outside, it's X. Then I have, what's the translation? It's a translation of vector 4, sorry, negative 4. It's going to go 4 left and 2 down. So I imply these things to the point 2, negative 5. It should hopefully turn out to be that point. So let's see what happens. I take this thing, reflect it over the x-axis. If I reflect that over the x, it will then become... I gotta think this in my mind. 2, negative 5, reflect over the x-axis will become 2, positive 5. Oh wow, I hope I do these wrong. Horizontal compressed by 3. That's going to take that point and change it to... Okay, horizontal compressed by 3 means the x-coordinate has to march towards the axis by that. Okay, so it's like divide that by 3. That 2/3 looks familiar actually as part of another thing. And then I have to translate this down that way. So subtract 4. Oh, that's my friend right there. And subtract 2. Guess what? I get the same point that I had before. That makes me feel good. Okay. That discussion feels like exactly what's about to happen when I do this one. So I think I'm going to do this one in class also. Okay. Whoops, only a couple things left to do. Yeah, this... Oh, why are we turning? Okay, let's. What if we had 2 graphs? We had to figure out what happens. So far, it's been like, here's the code, execute the code, and see what happens. Here's a before and after. What had to be the code that kind of happened? All right. So was there any? This is a good way to think about this too, because in the end we're gonna have to describe this in terms of reflection, stretch, translate. Like what happened from F to G to get things to do what they did. So this is a good kind of order of questions, I think. Did any dilations happen? Is it the same? Is it congruent from the beginning? And looking at the whole thing, it's like, no. I can tell it's not congruent. Like if you look at this little I don't know, this little curly part right here, it's bigger over here. Those are not the same size. And realizing that the stretches and the translates from the last page can kind of go in a different amount. Like they can be x can expand or contract a certain way, and y can expand or contract differently. We got to look at this kind of separately. So like the length left to right of that little straight piece and that little straight piece are the same. So I don't think there was any horizontal compression or stretch, but up and down I think there was. And we could look at this curly things. The curly things seem to go from a height of 3 to a height of, was that 4? No, is it 5? Oh, it's weird. Oh, I don't like that. Let's look at another one. We could look at the overall kind of range, the size of that. The overall range there was 8. The overall range now is 2, 4, 6, 8, 10, 12. Oh, okay, that was pretty nice. So it looks like there was a horizontal, sorry, that's not horizontal, up and down is vertical. Vertical compress of, sorry, not compress, expand. Expansion, it went from 8 to 12, so we had to multiply by 1.5 to get 8 to turn into 12. I mean, you could figure that out, right? That's 1.5. That's where I get that 1.5. That's the only kind of dilations that happened. And I wish they would have said expansions or contractions, because it's not dilation, because it's not going x and y the same way, but that's the geometry nerd in me. Okay. Was there any reflections overall from start to finish? Will my eraser work? Oh, it does. Fantastic. It keeps changing from eraser use to eraser, like, parameters, and I don't want that. All right. Is there any reflections that happen? Well, clearly there's a reflection this way over the y-axis. Does that mean there couldn't have been any other ones? Well, no. And if I look at the kind of up and down, it doesn't look like there's any x-axis reflection. It looks like there was only y-axis reflection. And y-axis reflection, okay, well, reflection over y. If I'm correct about this, reflection over the y-axis should be, well, we'll get to it later. We'll get to the coding later. How would the graph of f of x look under the dilations and reflections that you already did? So if I do the reflection and then the stretching, does it land right where that does? Well, no. That's why we do that first, and then we try to figure out after that where the translation is. The translation is always the hardest one to figure out, and you kind of have to execute the reflection and the dilations. I could have actually thought about this in either order, but I'm going to apply the reflection, and then I'm going to apply the stretching, and I'm going to see, that's the stretch, that's reflect. But to calculate them, you could look at them in either order. But I'm going to apply those two, and I'm going to use the results of those two to figure out, okay, what is the translation? Okay, so if I reflect this first over the y-axis, like this point's going to go here. The top of the curly thing goes here, so the little curl is. This point goes here. I get that. Like this is gonna. You could probably do this just as fast as I could. That's kind of what it looks like. But then if I was going to stretched it by 1.5. These things that are at a height of like 4, those go up to a height of 6. Let me change color. After the stretch, things would go up to like 6 there. The 3 goes up to 4.5. The -4 down here goes to 6. So it's kind of, the zeros stay where they are. So it's kind of here. And if you look really closely, that whole thing is just 1 unit south of where it needs to go. I need to translate up by 1 more to get it to go where it needs to go. So the translation that's needed is an up 1. Oh, I said that already. Okay. Write an equation. Okay. So the equation we need to write is reflect by reflecting over y. We just stretch by, what did we say? Vertical expansion by 1.5. And we need to translate by translating up 1. Okay, so coding wise, let's talk about each one of those things in terms of code. Reflecting over the y-axis means change the x. I believe that's this. Reflecting over the y-axis is f of -x. I hope I did that right. I always get that wrong. Vertical expansion and just by itself, just to vertically expand something by that much, I need to take 3/2 out front times f of x. And translate up by 1, I would take f of x and add 1. So putting all that into one code, I have to do this. 3/2 f of -x plus 1. I believe that's it. Okay, that's all. See you.